And so you can use that same type of thought process when she's introducing new variables, and you don't have to think, oh, what is that? You know, lowercase, uppercase, so on. All right, so just keep that in mind. Okay, first law of thermodynamics. For this exam, that's all you're going to use, for the most part, when you're computing work and energy or heat transfer. I know Dr. Harris says all the time, this is not a heat transfer class, and especially since I'm a civil engineer, I haven't had a heat transfer class. It's not required, right? So I don't know how to use heat transfer methods to get heat transfer, right? So we use the first law, right? This is the most basic fundamental law that you can use. Now, in this course, we deal with closed systems, right? So Dr. Harris refers to the piston cylinder, right? She's going to say that over and over and over and over, right? And I was on Google trying to find other closed systems, and I can't really find them too easily. It was 1 o'clock in the morning this morning, so I just said screw it and went to bed. But, you know, really the piston cylinder is the one you want to think about, all right? When you're on the exam, closed system, nothing else I'm dealing with except what's inside that piston cylinder. So, what we mean by closed system is no mass enters or exits when you're doing your analysis, right? So it's like a control volume, right? Fluid. How many of you guys have fluids? Okay, so you guys have all fluids, right? So it's all about the control volume analysis. This is just an example of a piston cylinder, right? In case you didn't know what that is, I'm sure you guys probably had a pretty clear idea. Now, this is the first law. The change in energy is equal to the heat transfer minus the work done, or inputted, or outputted by the system, or to the system, okay? It's the most fundamental law, all right? Now, so Q is heat transfer, work is done to by the system, E is total energy. We'll get to the signs in a second, all right? I want to remind you of something from Physics 1. When you took Physics 1, you probably remember Dave Wick talking about the conservation of energy between 2 points, right? So if I had like a roller coaster, right, and I call this point 1, and I call this point 2, then what we're doing is we want to calculate, say, from some data, right? We have some energy amount here, and we have some energy amount here. We have, say, velocity here and velocity here. And you had to write this energy equation between 2 points, and you wanted to find the velocity that the roller coaster would be at this point, or whatever, right? Now, if you remember, the equation looks something like this, right? That what we did was we said E1 is equal to E2, right? So the energy at this point is equal to the energy at this point. We had kinetic energy and potential energy, right? So kinetic energy was 1/2 mv squared, and potential energy was mg times whatever this height is, right? H, right? And if I remember correctly, because I actually talked to him a couple days ago, and I asked him this, I believe the way he teaches it in classes, he says, we disregard the internal energy in physics because that's an upper level course and stuff. So now in thermo, we're looking at internal energy, and we don't really care much about these, right? And I believe Dr. Harris would say something like, well, in most problems, if these values are given to you, neglect them, right? Or the problem will say the velocity is this much smaller than some value and you neglect it, right? And so on the exam, when you're doing the first law, neglect this value if you're not doing the values, right? Don't fret about, oh, I don't have a velocity value, or oh, I don't have a mass value, you know, what am I supposed to do? Write it on your paper. I'm going to assume that I'm neglecting potential and kinetic energy, all right? So again, neglect kinetic and potential energy. Now, what this equation then reduces to is delta, so I'm going to come over here and just get rid of this. So E is defined as kinetic energy plus potential energy plus U, right? So if we're going to neglect kinetic and potential, and we're going to look at the change in between 2 points, then therefore these two things are equal, right? So what do I have up here? Okay, I have delta U is equal to Q minus W. Well, Q minus W is equal to E, right? So this is also equal to Q minus W, right? So therefore I can equate these things, and that's how I get this. Okay, and you're always going to be interpreting these things between 2 states, all right? So if you're a little confused, that's okay. We'll definitely clear that up here, all right? Sign conventions. I would advise put this on your note card. She doesn't put this on surroundings. So think of the piston cylinder device, right? You have a gas inside and you're doing some sort of, volume, whatever, constant pressure process, what have you. And what ends up happening is the gas inside is doing work on the walls of the container, right? It's like expanding it or compressing it, right? And so this is where you need the sign. Sometimes in the exam problem, the wording is going to say something like, the work done by the gas onto the system is 33 kilojoules. So you have to interpret that negative 33 or positive 33. All right? And that's what's a pain in the butt. So go back to your notes and get these sign definitions on your sheet. The heat transfer is just the opposite. All right? So if you can understand the sign convention for work, heat transfer is opposite. All right? Okay, another big thing. PV diagrams. I don't think that in class they're described so easily for us to understand, so that's why I wanted to add a slide here. When you're looking at a PV diagram, when we look at the work, it's just the area underneath the PV curve, right? So if you go in the lab and you measure different volumes and pressures and you get a curve like this, then to find the work that is being done by the substance is just simply just calculus. It's really just integral from state 1 to state 2 of the pressure dV. Now, when I write on the board, I'm going to use this notation as a property, as capital P, right, as cubic meters. And I'm going to use this notation as cubic meters per kilogram. All right, and I had to figure that out fast when I was taking her class because her sign and the way she does her notation is very confusing. And so what you have to do is in class, you have to do a sign convention, a notation convention that works for you and stick with it. And that's how you won't get confused, at least for me. All right. The pressure may be constant or may not be constant. Okay, so it's kind of a function of the volume, right? Sometimes you're going to be given that, sometimes you won't. All right. So again, just kind of conceptual, just keep that in mind. All right. Now, PV diagram or TV diagram. What happened? I'm going to explain the difference, and this you should also put on your note card what the difference is between PV and TV, because on the exam she'll most likely have a problem where she'll ask you to plot the PV diagram and label things, right? And so I'll explain that a little bit later. Now, one of the most important things that you want to recognize from this curve is V out and V sub G. You guys know what those mean? Yeah. Exactly, right. So basically, I don't know why they use F here, but basically, at this point, V sub F, this is the point where you're going from compressed liquid, which is in this region, into this green region. And so basically, you're heating up to a point where what's inside here is going to be a mixture of gas and liquid. And that's why she calls it quality, right? X is quality, right? You have a mixture of gas and liquid, right? So whenever you're in here, you have a mixture. When you get to this point, V sub G, they call it V sub G because that's the hottest state where you're going to have the last bit of gas, right? When you come out here, this is superheat. It's all gas now, right? So I guess I should have said this is the last point where you're going to have gas. This is the last point where you're going to have liquid and gas. Does that make sense? And I'll show you how to utilize this with the table in an example problem, right? Because that's the most important, all right? So does everyone kind of understand that? So on your note card, what you want to do is you want to write down something like this, and you want to say that, this is the compressed or saturated, and this is quality. So this is liquid and gas, and this is superheat, right? Because this PV diagram is simply just a visual representation of all these tables. So if you can work between them, then it's easy, okay? And I believe your class note should have, when she introduced this, should have something like if the volume is greater than like V sub G, then you're in the superheated region. If you're in the compressed region, then the specific volume is less than V sub F, right? Less than the volume at this point, right? And that means you're in this region, right? Or you know you're in the quality region if you're between V sub G and V sub F, right? And so if you have that on your note card, then whatever problem she gives you, when you go to the tables to figure out what your first state is, you'll say, oh, okay, I'm at, V sub B is, 0.5 and V sub F is 0.3. Okay, I know I'm in this region. Okay, great. And then that's how you can kind of go through the process. All right, so this is visual representations. Everyone have any questions on this? Okay, just move down the process. All right, the other thing for your note card. Difference between PV and TV. There is no difference except the way in which the contour lines are drawn. Okay, these contour lines here are called isotherms or isobars, right? You've probably heard her say that in between, cops, right? Okay? So try to keep it a little funny here too. So if I have a PV diagram, then the contour, the temperature contours, the isotherms are going to come down like this, right? Don't argue, don't question it. I tried. Just go. Just put it on your note card and accept it and move on, all right? And you'll be fine, right? With the TV, notice that now the therms are going this way as opposed to this way, right? And it all has to do with that three-dimensional picture she showed you in one of the classes where no one understands what's going on and you're just kind of whatever, texting or whatever, okay? So what's important here is on your note card is to have your TV, like that, and you're going to have, say for the TV, you're going to have something like this, right? That's an isomer. And so when she asked you to show the process from state 1 to state 2, look at these arrows. So they're, in this diagram, they're saying state 1 is in the quality zone, right? In between this shaded region, right? And then state 2 is, say, right at VG, and then state 3 is superheated, right? And so you're going along the iso bar here, right? Iso bar, right? Because this is a TV diagram. Iso bar, isotherm. You don't have to know about that, okay? Just look at the contour, right?